We're going to look at specific types of exponential functions today that are called exponential growth and exponential decay. And let's first define what is exponential growth and what is exponential decay. So exponential growth is basically when a quantity increases by the same factor over equal quantities of time. Oops, let's make that a little bit better. So that's kind of a fancy way of saying, for example, if you deposit money in a bank, it's going to go up like 2% every year or something like that. So you have a constant increase, right? The same factor, so it's multiplying by the same factor every time. And then we're looking at a specific amount of time. So every year, every month, every 2 weeks, just some standard measurement. And this function, you'll see right here, it's kind of small, but it's y equals a times parentheses 1 plus r to the t power, where it's really important we know a, which is the initial amount. This is a. The rate of growth, it's always going to give you a percentage, but we want it in a decimal, so this is your r. Time is going to be a variable, so time is going to stay t in your function. And then the growth factor is just 1 plus r. Okay? So let's take a look at the first example, which deals with exponential growth, and then we'll come back and talk about exponential decay. So example A, the inaugural attendance of an annual art festival is 80,000. The attendance Y increases by 6% every year. We want to write an exponential growth function that represents the attendance after t years. So what we want to do is we want to make sure we know what part is what. So we definitely need to know a value for A and a value for R. So A will be the initial amount. So A is going to be the first group attending the festival. And then R should be the percent increase for exponential growth. So we increase by 6%. So R is 6%. But remember, we want this as a decimal. So that's 6 over 100, which is 0.06. All right. And then we're going to go ahead and substitute it into our exponential growth function, which remember is y equals a, then parentheses 1 plus r to the t power. And what, again, needs to get swapped out for numbers are a and r. So let's go ahead and rewrite that. So this turns into y equals 80,000 times 1 plus 0.06 to the t power. Then we want to simplify this growth factor to get y equals 80,000 times 1.06 to the t power. Okay? So there's our function. So now we can actually use it to answer questions. So the question here says, how many people will attend the festival in the 5th year? So this question is actually worded a little weirdly. So you might want to plug in t as 5. But remember, the first year we already have a number, which is 80,000. So note t equals 0 is the first year. So that means the 5th year is t equals 4. Okay, so that's just tricky here in the way they word it. If they said how many people attend after 5 years, then we'd plug in 5. Okay, so just be careful, watch out for the language. So now all we have to do is plug in 4 for t. So y equals 80,000 times 1.06 to the 4th power. And here's where your calculator comes in. Okay, so you're going to do this in your calculator, and you're going to get something like oops, 100,998.16, right? That's approximate. But we want to round to the nearest thousand position, which means we want to round to this value, right, where that first 0 is. So now let's go ahead and round up because the number after that is 9. So this is going to be about 101,000 people. Okay. And I ran out of space to write my sentence, but you'd want to finish your sentence off by saying there would be about 101,000 people attending in the 5th year. Okay? Let's go back up and talk about decay. So exponential growth is when we're increasing. So if you're thinking decay, decay means to decompose or to break apart. We're going to get smaller for exponential decay. So it's basically the same idea, but instead of increasing, we're going to decrease. So it's when a quantity decreases by the same factor over equal quantities of time. So you're going to want to recognize exponential growth and decay based on, is it getting bigger or is it getting smaller? All right. And then the exponential decay function is very similar, but the big difference is instead of 1 plus r, it's 1 minus r. But we're still looking for the same stuff, right? A is still the initial amount. R is still the rate of change, but this time it's how much we are decreasing, right? Again, in decimal form. Time will still stay t in our function. And then the decay factor is still something we want to simplify. So let's take a look at let's take a look at the next example. So a car initially costs $30,000. The value y decreases by 5% each year. Let's write an exponential, and this should say decay, not growth. Function that represents the value after t years. And we know it's decay because you'll see it's decreasing. Oops, that's not a highlighter. So we know it's decay because it's decreasing. Okay? So once again, start with identifying what we know. So the initial amount, A, the rate of change is the percentage, R, and again, we want this as a decimal, so that's 5 over 100, which is going to give us 0.05. And then we know the function is y equals a times 1 minus r to the t power. So let's go ahead and plug in what we know. So y equals 30,000 times 1 minus 0.05 to the t. Simplify that decay factor to get y equals 30,000 times 0.95 to the t power. And now we can use that to, apply that to questions, figure out how much that car is worth after 10 years, after 7 years, in the 6th year, whatever. Okay? So now notice the language in the question. It says after 6 years. So now we can be safe and say t equals 6, right? If we're asking like in the 6th year, right, then we would be using t equals 5. So we're looking after 6 years, how much is this thing worth? So plug in 6 for t, and then bust out your calculator. Order of operations, exponent first, so 0.95 to the 6th power, then multiply that by 30,000, and we should get something like 22,052.76. But now look back at the problem. I want you to round to the nearest 100. So where is the 100 position? The 100 position is right here at that 0. So I want to look to the right of it. 5 means we're going to round up, so this is going to be approximately $22,100. So let's go ahead and finish that off as a sentence because we have space this time. The price after 6 years is about $22,100. Okay? So that's exponential growth, exponential decay. Go ahead and try 1 and 2. All right? And 2, this should say decay. I'm not sure why we forgot to change those words. But write your functions and then use your calculator to calculate your values, and we'll come back and check your work. All right, so check your work. So check your function for 1, and then taking a look at how many members will there be in 2016? That's 6 years after 2010. So plugging in 6 for t, rounding to the nearest 10,000, we should get about 1,160,000. Okay, and then number 2, it's decreasing, so we know it's exponential decay. Check your function. And then if we're looking at 2012, that is 12 years after the year 2000, so t equals 12. And if we're rounding to the nearest animal, that's the nearest one animal. So rounding to the nearest ones, we know there's about 1,078 animals left in 2012. Okay, we'll finish the rest of this in class. Thank you for listening. Please come back with questions and make sure you know your decay and growth functions.